We're now going to focus on another type of function, and that's called a logarithmic function. We will look at how logarithms and exponential functions are related, and we'll write a logarithmic expression in an exponential expression. We'll simplify logarithmic expressions, graph basic log functions, and solve applications involving logs. If you remember one-to-one functions, we talked about that a couple sections ago related to inverse functions and discovered that one-to-one functions are functions that have an inverse function. And one-to-one function can be found by a graph that passes the horizontal line test. And so recall that the basic exponential function, f of x is equal to b to the x, where b is greater than 0 and b is not 1, is a one-to-one function, right? Its graph is either always increasing or always decreasing, so its graph passes the horizontal line test and therefore has an inverse function. And to find the inverse function, we will apply the steps that we did earlier. So if you remember, we replace f of x with y, so we'll get y is equal to b to the x, and then we have to interchange x and y, which gives us then, if you think about interchanging those, now then we get x equals b to the y. And typically our steps were then to solve for y. So how do we solve for the variable when it is in the exponent? We actually don't have any algebraic way to do that. But what this is saying is that y is the exponent of b that produces x. And so we actually need a new symbol, and we call it a logarithm, to denote this equivalent form of y. So the way we solve for y is we say that it is equal to log to the base b of x. But all that notation means is that y is the exponent of b that produces x. So when you see y equals log to the base b of x, you're thinking, well, b to what number is equal to x? And whatever that exponent is the value of y. So logarithm is just simply an exponent. So I want you to pause the video in just a minute, and I want you to use your calculator to find these values. On your calculator, you have one of the functions that is log, which is log. And I want you to find log 10, log 100, log 1000, log of 1, and log of 1/10. On the calculator, when you press the log key, you'll probably see a parentheses that opens, so you'll just need to close the parentheses after the input. Okay, and so you can pause your video now and find those values. Okay, so let's check to see what you found. Hopefully you got these values, that the log of 10 is 1, the log of 100 is 2, the log of 1000 is 3, the log of 1 is 0, and the log of 1/10 is -1. But you remember in our previous discussion, I just defined y equals log to the base b of x to mean that b to the y is equal to x. Well, one thing that we don't see in this particular function, right, there's no base that is explicitly defined. It's actually understood. And let's think about this. So we're saying that some number to the 1 gives us 10. Well, that has to be 10, right? 10 to the 1 is equal to 10. Some number squared is 100. Well, that's 10 squared is equal to 100. Some number cubed is 1000. Well, that was 10 cubed is equal to 1000. 10 to the 0 is equal to 1. And then 10 to the -1 is equal to 1/10. So this log function on your calculator is actually understood to be the log to the base 10 of x. What this function tells us is the exponent of 10 that produces x. Just to reiterate, log 10 is 1, log 100 is 2, log of 1000 is 3, log of 1 is 0, and log of 1/10 is -1. The inverse of the exponential function f of x equals b to the x, where b is greater than 0 and b is not equal to 1, is this log function f of x equals log to the base b of x, where b is greater than 0 and b is not equal to 1. So just in that previous example, if we think about f of x is equal to 10 to the x, then the inverse of that function is f of x equals log x. Right, so in 10 to the x, my input are the exponents, right? Like 0, 1, and 2. 10 to the 0 is 1. 10 to the 1 is 10. 10 squared is 100. But in the log function, my input is the 1, 10, and 100, and we just found with the calculator that the log of 1 is 0. The log of 10 is 1. The log of 100 is 2. So there again we see that x and y interchanging that we've talked about with inverse functions. The other thing that we need to think about is that the domain and range of a function and its inverse interchange also. So recall that the domain of the exponential function is all real numbers, right? That was negative infinity to infinity. And its range is from 0 to infinity. And so what that means is that the domain of the log function is going to be 0 to infinity, and its range is all real numbers, negative infinity to infinity. For a log function, we can only input positive real numbers, but the output will be any type of real number. Just a more official definition of a log. For b greater than 0 and b not equal to 1, the logarithm, or sometimes we just call it log, to the base b of x is denoted by y equals log to the base b of x, and this is equivalent to b to the y is equal to x for every x greater than 0 and every real number y. The value x is called the argument of the logarithmic expression. So this is the most important part of this to me. The way to relate a logarithm to its exponential form, y equals log to the base b of x, is equivalent to b to the y equals x. And I have a graphic here to kind of show you this. So y equals log to the base b of x means b to the y is equal to x. Right? So the base always stays the base. If it's the base of the log, it's also the base of the exponential expression. So here are some equivalent expressions that we can look at. We know that 2 cubed is equal to 8. So in a log form, we're trying to write a logarithm that states that 3 is the exponent of 2 that gives us 8. So we can write this as 3, right? The exponent is what a log is always equal to. 3 is equal to log to the base what? Well, the base was 2. 3 is equal to log to the base 2 of 8. So this means 2 cubed is equal to 8. If we have the exponential form 5 squared equals 25, well, we can write that in log form to say that 2, that is our exponent, is equal to log to the base 5 of 25. Again, that means that 2 is the exponent of 5 that gives us 25, right? 5 squared is 25. 7 to the negative 1 equals 1/7. To write that in logarithmic form, our exponent is what the log is equal to. So then we have log base 7, and then what the exponential form is equal to of 1/7. So this means 7 to the negative 1 is equal to 1/7. 10 to the 0 equals 1. So to write that in logarithmic form, we know that 0 is what the log equals, right? The log is the exponent. So we say 0 is equal to the log to the base 10 of 1. And to confirm, 10 to the 0 is 1. And then we just mentioned a minute ago that log to the base 10 is what the calculator is actually finding, and we write that as just the log without an explicit base. So we can say that 0 is equal to log of 1. So when the base of the log is 10, it's typically omitted, and we call log base 10 a common logarithm. we have some problems here that I want to rewrite from their log form or exponential form to its other form. In this table, our given statement for part A is a log of base 10 of 100,000 is equal to 5. So to write this in an exponential form means that 5 is a power of 10 that gives us 100,000. So this would be 10 to the 5 is equal to 100,000. Log to the base 2 of 16 equals 4. So this is saying that 4 is the exponent that 2 needs to be raised to get 16. And in the exponential form, that is 2 to the 4 equals 16. Log to the base 7 of 49 equals 2. So this is equivalent to 7 squared equals 49. Now here we have an exponential form. 7 to the 0 equals 1. So we want to write it in its log form. So in its log form, we think about log to the base what? Well, our base of that exponent is 7. And remember that the log is always equal to the exponent. So our log is going to be equal to 0. So this means log to the base 7 of what? Well, 1 is equal to 0. So to check, 7 to the 0 is equal to 1. Log to the base 81 of 9 equals 1/2. So the base of the exponent is 81. What the log is equal to is our exponent, and then that is equal to the argument, which is 9. So we write this as 81 to the 1/2 equals 9. And recall that 81 to the 1/2 is really the square root of 81, and that is indeed 9. Log to the base 2 of 1/8 equals -3. So the base is 2. The exponent is what the log equals, which is -3, equals the argument of the log, which is 1/8. So the equivalent form is 2 to the -3 equals 1/8. And remember your rules of negative exponents. 2 to the -3 is really 1 over 2 cubed, which is 1/8. E to the 1 equals E. So here's this number E coming up again. So that would be log to the base E, right? Our base of our exponent is E. Log to the base E of E is equal to 1, right? So the log is always equal to the exponent. The square root of 25 equals 5. Well, we might need to rewrite this, that the square root of 25 is really in exponential form. 25 to the 1/2 is equal to 5. So this is equivalent to the log to the base 25. Okay, so that's going to be equal to 1/2, right? It's equal to the exponent. The log base 25 of what? The log base 25 of 5 is equal to 1/2. And we can check that 25 to the 1/2 is 5. So to convert from logarithmic to exponential form, we're using y equals log to the base b of x is equivalent to b to the y equals x. X is called the argument of the logarithmic expression, and the argument always needs to be greater than 0. And one other thing about this is we talk about the base e, which we saw just a moment ago in that table. When the base of a logarithm is e, remember that we called e the natural exponential function, like y equals e to the x was a natural exponential function. Well, we can actually write it in a special way. When the base of a logarithm is e, we write it with the notation ln of x. So ln is read the natural log of x. That is, log to the base e of x is equivalent to ln of x. So that's just a case just like the common log, right? Log to the base 10 of x is equal to log of x, right? We don't write the base explicitly. Same thing here. If we see natural log of x, we're understanding that the base of the log is actually e. And so that in that previous example where we saw e to the 1 equals e, and we wrote it as log to the base e of e equals 1, well, instead of log to the base e, we can just write that as natural log of e equals 1. So common log, log base 10 is just log x. Log base c is natural log.